To begin the design phase, all 6 of the main bridge types were identified and analysed. This ensured that the group had a firm grasp on the mechanics behind bridges. The 6 bridge types that were studied include the truss bridge, arc bridge, beam bridge, suspension bridge, cable stay bridge, and finally the cantilever bridge. Each bridge has its own characteristics, but they are all subject to the tensile, compression, torsion, shear, and bending forces. Considering spaghetti is good under tension but weak under compression, 4 out of the 6 bridges were considered in the design phase. The beam was deemed unsuitable for a spaghetti bridge due to its design, which focuses more on bend and compression forces. Cantilever bridges would require too much spaghetti and would easily surpass the 200-gram limit, so both of these designs were ruled out. Historic bridges such as the Golden Gate Bridge, Sydney Harbour Bridge, and the Hangzhou Bay Bridge were researched to aid us in designing our own bridge design. The team did not want to copy an already designed bridge. We wanted to feel accomplished and completely design our own, which the following drawings were based off of. After slowly discussing and refining each design, an arc bridge was reached. This design was transferred to a software which would allow for the member forces to be accurately calculated. The software was called JF Matrix, and it was able to calculate what each member would experience force-wise under a specific load. The purpose of the arc bridge was to primarily utilize members under tension, and any under compression were kept short, as this helps spaghetti under compression. Although this was an effective design, according to JF Matrix, the team faced construction issues as we did not find a logical solution to securely join 9 separate members in a single location without disrupting the structural integrity of the bridge. This design was then scrapped. The group then attempted to construct a truss bridge, basically starting from square one, as we fell back to a truss design. The intent for this build was to keep it simple and light, ultimately competing for the weight-load ratio and not the heaviest load. The new design was drawn out on a 1.1 scale, and then once the group was satisfied with the design, it was then transferred to JF Matrix for it to be simulated. The result did not come back as expected, with 2 members across the top beam experiencing 8.50 kilonewtons of compressive force, while the bridge is under a 10 kilonewton load. The bridge was made anyways, however, it was not as simple as the group expected, as the final result was warped and did not sit flush on a flat surface. The bridge weighed 90 grams, but this was due to each member only being 2 spaghetti thick and the beam being 5. It was only able to carry 5 kilograms load before failure. This bridge design was also scrapped. The team was in need of a new method of supergluing the joints together. Luckily, a group member suggested we use brace plates made out of spaghetti. To form these brace plates, spaghetti was aligned parallel to each other with an approximate length of 2 centimeters. Once glued, 2 spaghetti pieces were glued to reinforce the brace plates. This new method of gluing joints together allowed us to revert back to the original drawing of an arc bridge. From the 2 main designs, the group fused both ideas to create the final design, which is an arc and truss hybrid. Once the team was satisfied with the rough sketch design, it was then drawn on an A3 paper, 1.1 scale, then transferred to JF Matrix. Once the forces were calculated, members in compression, which are the members highlighted in red, were calculated to experience a force of between 5 to 6.5 kilonewtons, resulting in these members being 8 spaghetti thick. Tension members, which have been highlighted in green, were calculated to experience a member force between 2 to 5 kilonewtons, in turn only requiring these members to be 5 spaghetti thick. With a refined final design, we were able to shorten 2 of the members from the original arc design, effectively reducing the overall weight while still receiving the same result in terms of member forces. The beam being influenced by the test conducted prior to the construction and mentioned in the report, were constructed out of 11 spaghetti. However, 2 bunches of 11 were combined in order to reach the required span of 350 millimeters, meaning that the beam would be 22 thick after the bunches of spaghetti had been overlapped and superglued. Interlocking the bunch of spaghetti reinforces the center of the beam, which is where the load will be applied. When gluing each member, we found it easier as a group to wrap the members in rubber bands before spot gluing them to ensure they do not move while drying and to form a strong bond between spaghetti strands. Once all of the members and brace plates were measured, cut to size and glued, construction for the spaghetti bridge could finally commence. To begin, 2 regular-sized brace plates and a large-sized brace plate were superglued to the beams. The normal-sized plates were glued on either end, while the large brace plate was glued directly in the center. The next step was to connect the central tensile members for the arch. This member was superglued on the center of the large brace plate. A square was used to ensure this member was perfectly straight, as this was a crucial element to the monitor during construction. If a member was not aligned correctly after it had dried, the bridge faces will not be symmetrical and misaligned when it's time to join them. The brace plates not only benefited the strength of the joints but also made constructing the bridge much more efficient. From this step, the plates were positioned according to the design of the beams. Once all the plates were in the correct position, the remaining members for the bridge face were laid over the plates in the correct position. This enabled the team to be cautious and not to rush this step, as it could easily cause an error without this method. The only part that proved to be a challenge was gluing the members that would eventually be used to join both of the bridge faces. Each member was glued and then held into position by hand, increasing the chance of human error. Again, a square was used to ensure these members were directly pointing upwards. One person would glue, the other hold it in place, and another group member would hold the square and direct the member into the correct angle. Once those members are firmly in place, the group was able to easily align the other bridge face on top of the newly added members. The other half fit like a puzzle, and we were able to apply glue to all connection points, which was later left to dry. The bridge was given a full 12 hours to dry before we returned to it, since that is the duration to wait in order for the superglue to reach optimal strength. Upon arrival of competition day, it was immediately recognized that our bridge was not able to correctly uphold the weight evenly, as the attachment was a plate instead of a hook. The plate required an even surface to sit on, with a hole for the hook to protrude through. Our bridge was in urgent need of modifications to fix the issue. Debris off of previously tested bridges was scavenged until the appropriate pieces were found. 2 members were found at the right length. These were then glued close to the middle in an attempt to distribute the weight evenly. However, this could not be fully achieved due to 3 members already glued to the center of the structure. The members that were glued on the day can be seen highlighted in green. On competition day, the bridge was able to carry a load of 22 kilos before failure. To our surprise, the bridge performed far better than the group predicted. In the event of failure, the bridge did not actually succumb to the load, but the members that were glued on competition day in order to hold the plate snapped. No damage was endured on the original bridge, only the members that were glued on the day. Although 22 kilos is a good score, the group was left speculating about what the true potential of the bridge's load capacity could have been. The ratio was 123% and placed 4th in class, meaning that the bridge was able to carry a load times 123 its own weight.